Welcome to you all to this session. Chapter number 2, video number 5. In this video, we are going to discuss the three topics: carnot cycle, carnot engine, and carnot principle. We will see one by one. Okay, the first topic is the carnot cycle. Before going to see in carnot cycle, we just recapitulate the previous concepts one by one. Reversible cycle. The name itself, it is a cycle. The cycle here, whatever the process consists in this cycle, every process should be a reversible process. Then only it is a reversible cycle. Isothermal process means the process occur at constant temperature. That is the isothermal process. If the heat is supplied at isothermal process, means heat transfer take place. If the heat transfer take place between the two bodies, body 1 and body 2, if there is heat transfer take place from body 1 to 2 at a constant temperature, body 1 and body 2 having a same temperature, then the heat transfer taking place, then only it is said to be isothermal process. It won't be in practical possible, but it is a theoretical or idealized process only. This is for the heat transfer take place between the two bodies having the constant temperature. It takes infinite time is required to transfer, infinitely slow process. Such for not only this, any reversible process occurs, it takes infinity time. It is a infinity slow process, we can say. Next is a adiabatic process. Adiabatic process means when the process is occurring, there is no chance of heat transfer. That is the Q should be 0 while adiabatic process. These three concepts is enough before going to the carnot cycle. Reversible cycle means every process in this cycle should be a reversible process only. Then only it is a reversible cycle. There are so many reversible cycles. The first convinced a reversible cycle by a scientist named Carnot in 1824. From the first topic is the Carnot cycle. The Carnot cycle consists of 4 reversible process. One is the isothermal heat supply. Second one is the reversible adiabatic expansion process. Third one is the reversible compression isothermal heat rejection process. Fourth one is the reversible adiabatic compression process. Here the work is supplied 1 to 2. It is indicated with heat supply. Q suffix S is the heat supply at constant temperature. That is the isothermal process. And heat rejected at isothermal process, heat rejected, Q suffix R is the heat rejected. This is the expansion process. The expansion work, it is the entropy constant. That is the reversible adiabatic process 2 to 3. Here is the reversible work compression. This is the reversible adiabatic compression work 4 to 1 process. 1 to 2 is the isothermal heat supply. 2 to 3 is the reversible adiabatic expansion work. 3 to 4 is the isothermal heat rejection process. 4 to 1 is the reversible adiabatic compression process. The cycle consists of 4 reversible process. Here the Carnot cycle, if we see one by one, first applying the first law of thermodynamics at each and every process. 1 to 2 Q 1 to 2 is equal to the internal energy 1 to 2 plus 1 to 2. For an isothermal process, internal energy U is equal to 0. Why means U is the CV delta T. Here for an isothermal process, temperature is constant, so dt term is 0, so U value is 0, so this value will be 0. 1 to 2 process, P dV integral P dV process 1 to 2. Here the medium taken as a ideal gas. Ideal gas, we know the relation PV is equal to nRT. P can be write from here, P equal to nRT by V, where can be write as a nRT. Here T1 is equal to T2, can be write it is a higher temperature, so higher temperature T suffix H. This is a lower temperature, T suffix lower temperature TL. T 1 to 2 at high temperature, I can write TH by V into dV integral process 1 to 2 can be write n r T suffix H ln of V2 by V1. If you write 2 to 3 process, applying the same 2 to 3 process. Here the process itself is a reversible adiabatic process. Reversible adiabatic process means there is no heat transfer take place, so Q term is equal to the 0, where U is the internal energy, can be write as a NCV occurring between the T2 minus T3 plus W2 to 3. From this way we can get W2 3 value as a NCV T2. Okay. Similarly, if you write 2 to 3 process also isothermal heat rejection process. If you write in this way, we will get nRT. Here at T is the lower temperature ln of V4 by V3. Here is the heat supply, so positive. Here it is the heat rejected from the system, so it is a negative. Can we write it as a Q3 to 4 nRL ln of V3 by V4. This is a Carnot cycle. From the first law of thermodynamics, we all know the internal energy from point 1 to it is completing at point 1 because of the cycle, so internal energy is 0. Now the sum of work transfer is equal to the sum of heat transfer in a cycle for a cyclic process. So efficiency of Carnot cycle can be write as a W net to heat supply, where W net is equal to the W net is equal to the sum of the heat transfer. The heat transfer here, it is the Qs minus Qr. Can we write Qs minus Qr? This is the carnot cycle efficiency. Carnot cycle efficiency. If you rewrite here, now I am writing carnot cycle is equal to the 1 minus Q heat rejection to the heat supply. Heat rejection is the 3 to 4. 3 to 4 we know 1 minus N R T suffix L is ln of V 3 by V 4 to the heat supply L R T H ln of V2 by V1. We know from the adiabatic relations are PV per gamma is equal to constant, TV per gamma minus 1 is also constant. Using this relation, if you write the equation 2 to 3 process T2 V2 per gamma minus 1 is equal to the T3 V3 per gamma minus 1. Here if you rewrite here T3, this is simplification only, not more than that anything I am doing here. Gamma per minus 1, where T3 is the lower temperature, T2 is the higher temperature. Similarly, writing the 4 to 1, that also a reversible adiabatic process. So T4 V4 gamma 4 minus 1, T1 V4 V1 gamma minus 1. I can write this, and now T4 T1 is equal to the V1 by V4 gamma minus 1. T4 is the lower temperature, TL by T high temperature. Okay, from this to this value and this value becomes equal. So I can write V2 by V3 is equal to the V1 by V4. From this V3 by V4 can be write as a V2 by V1. We got this relation from the adiabatic relations. V2 by V1 is equal to the V3 by V4. V3 by ln of this value and this value is same, get cancelled. Now the efficiency of the carnot cycle can be simplified. NR get cancelled. T suffix L by T suffix H. This is the carnot cycle efficiency. When this cycle is applied, when the cycle is using in any engine, that engine is called as a carnot engine. This carnot engine is not a practically applicable. Why? Because for a execution here, when there is a heat supply, the process should be occur under a isothermal process. For this we need a perfectly conductor material is required at the cylinder head. For this, and at constant temperature, that is the source and receiver should be at a same temperature. In that process, the heat transfer to be take place means it requires a infinity amount of time. So it is very slow process, and lot of time is required for this 1 to 2 process to be happen. Okay, for the 2 to 3 process means it should be act as a perfectly insulator. Why? Because this is a adiabatic process. For adiabatic process, q should be the 0. at this process at the cylinder head, the material should be act as a perfectly insulated material. This both process should be act that too alternatively. In this universe there is no material which act as a alternatively. one one as a perfectly conductor, another one is a perfectly insulated material for this type of execution of the cycle. So there is a no chance of material is available in the universe which act as a perfectly insulated and perfectly conducted, that to an alternate process. So this is not possible in execution in the nature of carnot cycle. This is one of the reasons. Second reason is that for a isothermal process, heat transfer should be take place at constant temperature. It takes a infinity slow process, that too okay, infinity slow process. The piston okay, it takes infinity slow process. That is example, the piston have to run at 10 rpm. In the adiabatic process, the there is no heat transfer take place. So it should be process should be done as quick as possible, that is a 1000 rpm. The mechanism should be the mechanism of crank should be do the mechanism. One stroke at 10 rpm and second alternate stroke is the 1000 rpm. There is no mechanism is executed till now that when the two mechanisms should rotate at one is a slow process, another one is a very quick process. Such a mechanism till now not executed. So this two reasons it is not possible to execute a carnot cycle, but this is a used as a reference engine only, the carnot engine. Next one is the carnot engine. This is the theory. What is the theory is enough. Next is the carnot theorem. The next topic is the carnot principle. This is also called as a carnot theorem. There are the two theorems of carnot theorem. These are the two consequences of second law of thermodynamics only. First consequence of or first theorem of carnot theorem is that there is no there is no heat engine which is more efficient than there is a heat engine. In simple words, there should be no heat engine which efficiency of heat engine is getting more than that of heat engine getting a reversible heating engine. That is, in the nature there should be a no heat engine efficiency is more than heat engine of reversible heat engine. Okay, the first principle of carnot is that there is no heat engine operating between the same two thermal reservoir cannot have more than efficiency that the reversible heat engine operating between the same reservoir. Understood? What are you telling? This is a reversible heat engine. This is a it is a irreversible heat engine. This heat engine getting more efficiency. There is no heat engine which is getting more than this efficiency. From the carnot there is a consequence that when the two heat engines operating at the same two thermal reservoirs, there is no heat engine is executed in the nature getting more efficiency than the reversible heat engine. always reversible heat engine only getting the more efficiency. That is the first theorem of the carnot principle we are going to prove. Our aim is to show a reversible heat engine getting more efficiency than any other heat engine. For this, let us consider a non-reversible heat engine getting more efficiency than the reversible efficiency. This we are considering and we are proceeding. From the previous concept we know the efficiency of the engine is the W net to the amount of heat supply Q1 is more than W of Q1. Here if you observe, both having the same thermal reservoirs at the sink and source, two heat engine operating in between two thermal reservoirs, and both heat engines heat supply is the same, that is a Q1 and Q1, and work is done by the reversible heat engine is the W suffix R, or this is the reversible work, and this is the work from the this heat engine. From this, if you let, we are taking a reverse and starting the problem. Okay, here work from this relation W is more than reversible work from this. So this is a reversible heat engine. So by the reversible heat engine means the process can be reverse and can be reverse. Both heat and work are interact here will be the same, only the directions are changed. Now I am changing, now I am simply reversing the direction of the heat engine. Simply I am reversing this. So now this is acting as a heat pump. Whatever the energy is required to run the heat pump, it is collecting from the W net producing of heat engine W. Why? Because from this W is more than WR, even though some part of is left, that is a W net. W is generating from here and we are utilizing to run the heat pump. We are utilizing this, and left is giving here. Okay, now it is running. Okay, if you see, observe at the source, the heat transfer, the net heat transfer heat is here is 0. Why? Because Q1 amount of is collecting and Q1 amount of is withdrawing. So here Q net is 0. We can write as a, we can eliminate this as source. Why? Because this Q1 can be utilizing here directly and it is running. Okay, if you see, observe, with only one thermal reservoir the cyclic operation is occurring and producing a continuous amount of W net. This is the violation of the Kelvin Planck statement. That is the only with a single thermal reservoir there should be a work. The heat cannot be converted as a work. It is a violation of the second law of thermodynamics. So this is a wrong. So whatever we taken, it is also a wrong. So no heat engine efficiency is not greater than the reversible heat engine. So this is a wrong. So by this we can tell the reversible efficiency of the reversible heat engine is greater than any other heat engine when it is important, when it is operating between the same thermal reservoirs, then only the reversible heat engine efficiency is more. The second theorem is that The second Carnot theorem is that when all the reversible heat engines, this is R1 indicates the reversible heat engine 1 is the R1, R2 is the reversible heat engine 2, reversible heat engine 3. When all the reversible heat engines operating between the same thermal reservoirs having the same efficiency, it is only depends upon the end temperatures, not on the medium. This is the second theorem of the Carnot principle. When all the reversible heat engine operating between the same thermal reservoirs having the same efficiency, their efficiency is independent of the nature of the working fluid, which is only depends upon the end temperature of the reservoirs. So it is. Thank you.